Hey students, this is lesson 721, inequalities. This is a nice little chart for you just to remind you of what the inequality symbols are: less than, greater than, less than or equal to, greater than or equal to, and some samples of using them. A lot of times students will say, I don't remember if it's less than or greater than, so this is a good resource for you. Okay, in this first investigation, we're going to learn how to understand the symbols and the representations of inequalities. And uh, and so let's just think about this for a moment, and you can pause at any time to try and answer these questions. But the first question says, how is the meaning of 7 is less than x? And this is a less than symbol right there, similar to or different from that of x is greater than 7. So pause if you want to think about that. When we put 7 on first and then is less than x, what we're saying is 7 is less than all the solutions to this, all the x values. When we turn it around, we say all the values of x are greater than 7. They really are the same numbers. They're just two different ways of stating that. So, and I'll just write this down. The way we would write this out is we would say all numbers greater than seven. So we're talking about numbers like 7.5, 8, 8.5, 9, those kinds of numbers. All right, and sometimes we combine two inequalities. And when we do that, we call that a compound inequality. All right, and what do you think that means? If you say it, you're going to say 7 is less than x is less than 10. So, and notice one thing, x is actually in between there. So we're really talking about numbers that are, we can separate this into two things. We're talking about numbers where 7 is less than those numbers, and at the same time, the numbers are less than 10. So, or we can turn that around and just say numbers that are greater than 7 and less than 10. Now, values that would make that true are just numbers between 7 and 10, like 7.2, 8 is a good one, 9, anything up to like 9.9 or things like that. All right? So it says thermostats are used to control the temperature in a room or a building. How do you think a thermostat might use inequalities to do this? Well, let's say your temperature is set at 70 degrees. A room will get warmer and colder, so it's impossible for a furnace to keep it at exactly 70 degrees. So what it might do is, if you set it at 70 degrees, it might turn on at 69 degrees, and then it'll keep heating it up till it gets to 71, and then it'll kind of keep that range of plus or minus 1 degree in there. So we can use a compound inequality to represent that. If it shuts off when it hits 69, the temperature can go as low as 69. So we can say the temperature is greater than or equal to 69, and the temperature, if it can go up to 1 degree more, then we say 71. All right, so let's do a couple problems here. I'll skip over some, and you can go ahead and do those. But A says list 6 whole numbers that satisfy the inequality n plus 1 is less than 11. So we're going to think about that. We have a whole bunch of numbers, and when we add 1 to any of those numbers, we're still less than 11 total. So a number like, I don't know, 7, 8, or 9, because when we add 1 to each of those, we are still less than. Sorry, I had to get the phone. Anyway, so when we add 1 to 7, we get 8, and 8 is definitely less than 11, right? So you can see here that any number will work up to 10. 10 won't actually work because, and this is a good thing to know, if we add 1 to 10 and say that is less than 11, that is not true because 11 is not less than 11. So that's not true. But you can also use decimal numbers like 7.2 and things like that. All right. So number 2 says, consider this statement: k is less than or equal to 14 and greater than 9. Write the statement in symbols. I would suggest you pause right here and then go ahead and try it. So k is less than or equal to 14. And I'm just writing it straight in symbols. And k is greater than 9. It would look like that. Or it's nice if you can put them all into one simple thing. So we know 9 is the smallest. I'm going to put that first. K is greater than that, so it'll look like that. So 9 is less than k. And k is less than or equal to 14. So that compound inequality works for that. List all the whole numbers for which the inequality in part A is true. And I'll let you finish this up, but the first whole number that makes this true is 10. So 10, and then we're going to keep going up until the last number that works here is 14, because 14 is, this little line here means it can actually equal 14. But it can't equal 9 because it doesn't say less than or equal to 9 there. All right? Consider this: the inequality 15 is less than or equal to m is less than or equal to 18. Write this in words. So the way I would write that is m has to be bigger than 15, so I would write, and instead of m, that actually is a bunch of numbers. So I'm going to say all numbers that are greater than or equal to 15 and less than or equal to 18. And then it says list all whole numbers for which the inequality is true. I'll let you do that. Are there any other numbers, not necessarily whole numbers, for which the inequality is true? If so, give some examples. So numbers between 15 and 18 that aren't whole numbers, sure, like 15.2. Number 4 says, if you consider only whole number values for n, 4 of the 5 statements below represent the same values. Which equality below is not equivalent to the others? So this first one, 10 is less than n is less than 20. If we're only looking at whole numbers, then this one, 11 is the first whole number that works here, and 12 and 13, and I'm going to go all the way up to 19 for that one. Now if I look at this, 11 is less than or equal to n is less than or equal to 20. The first whole number here that works, since we have this equal sign, is 11, and 12 works, and 13, and this one goes all the way up to 20 also. Oops, I wrote that down wrong. That one goes all the way up to 19. So the numbers for this set are exactly the same as the numbers for the first one. So those two are the same. I'm going to let you find the one that's different. All right. Some problems to do. List 6 values, not necessarily whole numbers, that satisfy each inequality or pair of inequalities. I'll just pick a couple of them here. So we're talking about 6 values. Let's look at this second one, this number 6 here. It says q is greater than or equal to 12 and q is greater than 15. So if it's greater than or equal to 12, I'm thinking of a number like 13. But the word and means it also must be greater than 15. Since 13 is not greater than 15, that doesn't work. 14 doesn't work. 15 is not greater than 15. The first value that's a whole number that works is 16. 16 is greater than or equal to 12, and it's greater than or equal to 15. Numbers like 15 and a half also work, and so on. Okay, look at a couple more of these. Here we have an absolute value. That absolute value, remember, turns all negative numbers positive and leaves positive numbers positive. So we need those numbers to be less than 20 but greater than 17.75. So, and since we have equal signs, we could actually use a number like 20. We could also use a number like negative 20 because the absolute value will make that 20. I'm going to let you finish that and find the other 4 values. Here we're going to multiply 3 times some number, and we want that to be greater than 12. And I mean, since we're talking about greater than, we could pick some obvious numbers like 100. 3 times 100 is 300, and 300 is obviously greater than 12. Here you have to square the numbers, and they have to be greater than 0 to begin with, so that means positive numbers, and when you square them, they're less than 16. And you might think, well, 1 squared works, right? Because 1 squared, 1 times itself is 1. 2 works. 3 works because 3 times 3 is 9. 4 works because 4 times 4 is equal to 16. We can't use any numbers higher than that, though, so we're going to have to use some decimal numbers in between there, like 2.5 would be good. All right, so you're starting to get comfortable with inequalities. So let's take some statements and turn those into inequalities. Number 10 says a box of matches contains at least 48 but fewer than 55. Write an inequality for the number of matches and in a box. So you have to know what at least means. And so think about this. Does at least include 48 or not? And I think it does. So that means that we need to use greater than or equal to. So we can write n is greater than or equal to 48. And it says fewer than 55, so there's like a maximum amount there could be. And fewer does not include 55, so we're going to say and n is less than 55. It's nicer if you can combine those into one compound inequality. So 48 is less than or equal to n is less than 55. Works good for that one. Okay. Number 11, Tamika expects from 100 to 120 people to buy tickets to the talent show. Each ticket costs $5. Write an inequality to represent the total amount of money M she expects from ticket sales. The money she gets is actually 5 times the number of people that show up or the number of tickets she sells. So keep that in mind here. Now we know that she's expecting anywhere from 100 to 120 people. So the number of tickets she sells is going to be at the lowest amount 100 and no more than 120. So that would look like that. But the amount of money she gets is 5 for every ticket she sells. So I need to multiply these by 5. And when I do that, I get $500 would be the least she's going to get. And 5 times t is equal to the money that she gets. And the most she would get is 120 times 5, which is 600. Okay. I think I'm going to do number 12 in class. I like that one. Talk about that. Let's do number 13. Here we have an area problem. It says you can buy square tiles in a variety of sizes with side lengths ranging from 2 to 20 centimeters. Write an inequality to represent the range of possible areas. Okay, so these are squares, and a square is a rectangle, so you just have to multiply length times width to get the area. But with a square, length and width are the same. So our area is really the side length of the square times itself. Now the tiles, the smallest size is 2 centimeters, and the biggest size is 20 centimeters. And so we need to square those sides to get the area. So I'm just going to do 2 squared, s squared and 20 squared. And when I do that, I get 4 is less than or equal to s squared, which is our area, is less than or equal to 400. All right. I think I'll do number 13 in class. Let's do one more here. Number 17, an architect estimated that the maximum floor area for a square elevator in a particular building is 4 square meters. Building regulations require that the minimum area be 2.25 square meters. Write an inequality for the possible side lengths S of the elevator floor. So the elevator floors are squares. So our area, again, is equal to S squared, but we want side lengths this time, so we need to do the opposite of that. We need to do the square root of the area to get the side length. So here's our areas. The smallest area is 2.25, and that is less than or equal to our area, which has to be less than or equal to the maximum area, which is 4. And then we need to do the square root of both of those to get the side lengths. And that gives us 1.5 is less than or equal to the square root of the area is the side length is less than or equal to 2. All right, I'm going to end the lesson there, and we'll do the rest of them in class. See you tomorrow.